4.2 light years, 25 trillion miles. At the speed of our fastest spacecraft, Voyager 1, the trip to Proxima Centauri would take more than 70,000 years. You're staring at the closest star to Earth, and the math keeps saying no. Tonight, we map the journey. A laser array powerful enough to vaporize steel. A fusion engine that eats helium mined from Jupiter. A starship so heavy it must be built in orbit. If you enjoy mission briefings like this, subscribe and stay with the crew. Strap in, we begin. Picture a car on a highway, cruising at 70 miles per hour, never stopping for fuel, never slowing for weather, never leaving the road. That car would reach Proxima Centauri in about 40 million years. The driver's descendants, 40,000 generations later, would finally see a red dot on the horizon. That is our nearest star, the next closest point of light beyond our own star system, and the distance is already impossible. 4.2 light years. Written out, the number looks small. Spoken aloud, it sounds almost reachable. But a light year is the distance that light itself travels in 12 months, moving at 186,000 miles every second. Multiply that by 4, and you get something the human brain refuses to hold. Try this instead. If you shrank our home star down to the size of a marble and placed it on a table in New York, Proxima Centauri would be another marble sitting in Tokyo. Between those two marbles, nothing. No planets, no gas, no reference points. Just dark vacuum, colder than any place on Earth, stretching across the Pacific and halfway around the planet. 25 trillion miles. That is the real number. 25 followed by 12 zeros. The fastest object humans have ever built is a spacecraft called the Parker Solar Probe. It whips around our star at about 430,000 miles per hour, using gravity from Venus to slingshot closer with each pass. Nothing we have made moves faster. And if we aimed Parker directly at Proxima Centauri the moment it hit peak velocity, it would still need more than 6,000 years to arrive. 6,000 years. That is longer than recorded civilization. Longer than the pyramids have been standing. If the Egyptians had launched Parker when they cut the first limestone block for Giza, the probe would still be flying. It would still have another 1,500 years to go. Now think about Voyager 1, the probe that left Earth in 1977, carrying a gold record meant for alien hands. Voyager 1 is the farthest human object from home. It crossed the edge of our star's influence in 2012, entering true interstellar space. And it moves at roughly 38,000 miles per hour, which sounds fast until you do the division. Voyager 1, pointed at Proxima Centauri, would need over 70,000 years to cover the gap. The probe will not make it. Its radioisotope generator will run out of power by the 2030s, and its signal will fade to silence. The hardware will keep drifting, frozen and dead, for the rest of time. This is what engineers mean when they say the stars are unreachable. The distance is not just large, it is a category of size that every propulsion system we have ever built fails to address. We do not need a faster rocket, we need a different physics. And yet there are teams right now funded and working who believe it can be done. They have blueprints, they have equations. They have identified the exact obstacles standing between us and that second marble in Tokyo. The first obstacle is the one that has haunted rocketry since its invention, the tyranny of fuel mass. And once you understand it, you will see why every chemical rocket ever launched is, by definition, a dead end. Before we talk about the math that kills every chemical rocket, you need to understand what fast actually means in space. Because your intuition is lying to you. Voyager 1 is currently moving at roughly 38,000 miles per hour relative to our star. That figure sounds enormous. It is about 50 times faster than a rifle bullet. It is nearly 200 times faster than a commercial jet. If you stood on Earth and watched Voyager pass overhead, you would not see it. Your eyes could not track anything moving that quickly, and yet, at that speed, the probe covers only 184 miles every second. Our nearest star sits 25 trillion miles away. Do the division, and the mission clock reads roughly 73,000 years. That is the Voyager problem. It is the fastest thing humans ever sent toward deep space, and it is still moving at a crawl. To reach Proxima Centauri within a single human lifetime, a probe would need to travel at roughly 10% of light speed. That is 67 million miles per hour, almost 2,000 times faster than Voyager. Let that settle for a moment. Not twice as fast, not 10 times. Nearly 2,000 times the speed of the fastest thing we've ever launched. And Voyager only reached its current velocity by using gravity assists from multiple outer planets, a trick that took years of orbital choreography and perfect planetary alignment. You cannot get to 10% of light speed with gravity assists. The planets in our solar system do not have enough gravitational pull to deliver that kind of acceleration. You could loop Voyager around every world we have, and it would still fall short by a factor of hundreds. Here is where the engineering gets harsh. Every rocket we have ever built runs on the same basic principle. Throw mass out the back, and the rocket moves forward. Newton figured this out 3 centuries ago. The faster you throw the mass and the more of it you throw, the more your rocket accelerates. Simple. The problem is that carrying fuel costs fuel. Every kilogram of propellant you load into the tanks is a kilogram you must also accelerate, so you need more fuel to accelerate that fuel. Which means more fuel to accelerate that fuel. The cycle compounds fast and it compounds badly. Engineers call this the rocket equation. It is the equation that has ruled spaceflight since the first hydrogen-oxygen engine fired, and it has a cruel conclusion. To reach even a few % of light speed using chemical rockets, you would need a spacecraft the size of a moon. The fuel requirement grows exponentially, not linearly. Double your target speed, and the fuel mass does not double. It explodes upward by factors of thousands. This is why Voyager is stuck at 38,000 miles per hour. That was the ceiling. Even with 4-stage separation and every clever trick mission planners had available, that was as fast as chemistry could push a probe built in the 1970s. The tanks were empty. The physics had spoken. To break past this ceiling, we need to abandon chemistry altogether. We need an energy source so dense that the rocket equation stops mattering, and the candidates on the table get stranger and more terrifying with each passing decade. The first candidate involved riding atomic bombs. Here is the equation that every interstellar engineer hates. A rocket's final speed depends on 2 numbers: how fast the exhaust comes out the back, and the ratio of fuel mass to empty spacecraft mass. Sounds manageable? It is not. The trap is in the ratio. If you want your rocket to reach twice its exhaust velocity, you need to carry about 7 times as much fuel as empty spacecraft. Want to reach 3 times the exhaust velocity? Now you need 20 times the fuel. 4 times the exhaust velocity needs 55 times the fuel. The curve goes vertical fast. Each incremental boost in final speed demands an enormous jump in propellant mass. Picture a spacecraft with a dry mass of 1 ton. That is the probe itself. The cameras, the antennas, the computers. Now you want that 1-ton probe to reach 10% of light speed. Using the best chemical rocket fuel humanity has ever produced, the liquid hydrogen and liquid oxygen combination that powered the space shuttle, the exhaust velocity is roughly 10,000 miles per hour. 10% of light speed is 67 million miles per hour. Divide those numbers, and you need your rocket to reach 6,700 times its own exhaust velocity. Plug that into the rocket equation, and the required fuel mass becomes a number with thousands of digits. Written out, the fuel mass exceeds the mass of every atom in the visible universe. You would need more hydrogen than exists in every galaxy combined, just to push 1 ton of hardware to Proxima Centauri at cruising speed. This is what engineers mean when they say chemistry cannot get us there. They do not mean it would be expensive. They do not mean it would be difficult. They mean it is physically impossible. The fuel does not exist in the observable cosmos. You might think, fine, let us just accept a slower trip. Run the numbers at 1% of light speed instead. The required fuel mass drops, but only a little. You still need more propellant than fits inside our own planet. Drop the target to Voyager's current speed, and the math finally becomes tractable. That is exactly the speed Voyager achieved, and it is why the probe will need 70,000 years to cover the distance. The rocket equation gave us what we asked for. Engineers have spent decades trying to cheat this equation. The first serious attempt came from a simple observation. The exhaust velocity is the real bottleneck. If you can throw mass out the back faster, the fuel requirements collapse. Chemical reactions release energy by rearranging electrons in atoms. That is a small amount of energy per kilogram of fuel. Exhaust velocity tops out around 10,000 miles per hour. Hard ceiling. Nuclear reactions release energy by rearranging the atoms themselves. That is millions of times more energy per kilogram. The exhaust velocity climbs accordingly. Suddenly the fuel requirements become manageable instead of cosmic. This is why every serious interstellar proposal uses nuclear propulsion in some form. Fission, fusion, antimatter. Each one unlocks a different rung of the exhaust ladder, and each one brings new problems that are almost as impossible as the ones they solve. The first team to attempt this was a group of American physicists in the 1950s. Their plan was to detonate nuclear bombs directly behind the spacecraft, and somehow ride the blast. Here is one last way to feel the chemical rocket dead end. The Saturn V, the machine that carried Apollo astronauts to the moon, is still the most powerful rocket America has ever flown operationally. It stood 360 feet tall. It burned through 15 tons of fuel every second during launch. Its thrust at liftoff was 7.5 million pounds. Everything about it was engineered on a heroic scale. And all of that power delivered 3 astronauts, a command module, and a lunar lander to a rock that sits roughly 240,000 miles away, just barely past our own atmosphere, astronomically speaking. The moon is so close that radio commands reach it in under 2 seconds. Now stretch that trip. Keep the Saturn V. Point it at Proxima Centauri instead. Press ignition. The rocket could not get there. Not in 1,000 lifetimes. Not in 1,000,000. Even if you stripped the payload down to a single grapefruit-sized probe, even if you added every gram of fuel the first stage could physically hold, even if you ignored the fact that chemical rockets cannot coast for decades without tank failure, the math still laughs at you. The Saturn V's final coast speed, after all stages burned out, tops out near 25,000 miles per hour, worse than Voyager. This is not a failure of engineering ambition. It is a failure of the fuel itself. Liquid hydrogen and liquid oxygen, mixed and ignited, release about 10,000 joules of energy for every gram burned. That sounds like a lot until you compare it to what the atom can offer. A gram of uranium split through fission releases roughly 8 billion joules, not 10,000, 8 billion. The ratio is staggering. 1 gram of uranium holds the equivalent energy of about 800,000 grams of rocket fuel. Fusion is denser still. A gram of deuterium fused into helium releases around 300 billion joules. That is 7 times more than fission and 30 million times more than chemistry. Matter-antimatter annihilation sits at the top of the ladder. When a gram of antimatter meets a gram of ordinary matter, the pair releases 90 trillion joules. 900 billion times more energetic than the same mass of rocket fuel. The total energy from 1 gram of antimatter combined with 1 gram of matter would match the yield of a 40 kiloton nuclear weapon, twice the bomb dropped on Hiroshima. So the interstellar problem reframes itself. We do not need more rocket, we need more energy density. The fuel must deliver thousands of times more push per kilogram, or the rocket equation eats the mission before it leaves Earth orbit. Every serious Starship proposal on the table accepts this reality. Every one of them abandons chemistry. The moment you commit to interstellar distances, you commit to harnessing the nucleus, or to something even more exotic. Which means the Starship is no longer a rocket in the traditional sense. It is a controlled nuclear event, wrapped in metal, aimed at a star. The engineers who first worked out the details in the late 1950s did not flinch from that description. They embraced it. They proposed dropping actual nuclear bombs out the back of the ship, one after another, and letting the explosions kick the vessel forward. The project had a code name, Orion, 1957, Los Alamos National Laboratory. A team of physicists, including the Hungarian-American nuclear designer Stanislaw Ulam, sketched out a propulsion system that would haunt interstellar studies for the next 70 years. The idea was straightforward and terrifying. Build a spacecraft with an enormous metal plate on the back. Eject atomic bombs, one at a time, from a port at the rear. Let each bomb detonate a few hundred feet behind the plate. The blast wave slams into the plate absorbs the shock through massive springs, and the spacecraft leaps forward, then do it again and again. A bomb every few seconds, hundreds of them, thousands. A steady cadence of nuclear explosions shoving the vessel through space. The project was christened Orion. By 1959 it had a serious budget, a serious team and serious calculations. The lead designers included Freeman Dyson, one of the most respected theoretical physicists of the 20th century, and Ted Taylor, a former weapons designer who understood bomb physics better than almost anyone alive. Their numbers were shocking. A mature Orion vehicle could deliver a crew of astronauts to Mars in 6 weeks, to Saturn in a single year, and to Proxima Centauri in a configuration using pure fusion bombs in roughly 130 years, fast enough to arrive within 2 or 3 human lifetimes, slow by science fiction standards, fast by any propulsion engineer's reality. The math worked. That was the most disturbing part. Orion was not a fantasy. The team tested a scale model powered by conventional chemical explosives, and it flew. A small metal puck, pushed by a series of carefully timed charges, rose into the New Mexico sky in 1959. The footage still exists. The principle was proven. Dyson himself later described the project as the only realistic interstellar design ever produced using 20th century technology. No speculative physics, no undiscovered materials. Just a very large ship, a very large stockpile of nuclear weapons, and a very large pusher plate. Then the problems arrived. The first problem was fallout. Launching Orion from the ground would release enormous amounts of radioactive material into the atmosphere. Dyson's own calculations suggested that each launch would cause a statistically measurable number of cancer deaths worldwide. The project's leadership proposed launching the ship from remote ocean platforms or assembling it in orbit using conventional rockets. Both options added cost. Neither eliminated the core issue. The second problem was political. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Nuclear Test Ban Treaty. The treaty forbade nuclear detonations in the atmosphere, underwater, or in space. Orion required thousands of nuclear detonations in space to function. Overnight, the project became illegal under international law. The treaty did not explicitly mention propulsion. The intent, however, was clear. Nobody wanted atomic bombs going off anywhere above the ground. Orion was shelved by 1965. The team scattered. The design files were archived. The hardware testing stopped. And yet Orion never really died. The math remained too good to forget. Every subsequent interstellar study, every fusion starship proposal, every deep space concept paper traces its lineage back to that pusher plate and those calculations from Los Alamos. The project proved something crucial. Getting to another star is not physically impossible. It is only politically, economically, and morally impossible. That distinction is worse than it sounds. 1973, London. A group of British engineers and physicists, members of the British Interplanetary Society, sat down to answer a specific question. Using only technology that seemed reachable within the next century, could humans build a real, functional starship? Not a fantasy, not a cartoon, a working interstellar probe designed with proper engineering rigor, complete with fuel flow rates, heat management, structural tolerances, and mission profiles. The study ran for 5 years. The team was led by Alan Bond, an engineer who would later become famous for proposing a reusable spaceplane design. The final report, published in 1978, filled hundreds of pages. The project was called Daedalus, after the Greek inventor who built wings from wax and feathers. The result was the most detailed starship blueprint ever produced, and the numbers were staggering. Daedalus would launch from Jupiter orbit, not Earth, Jupiter, because the ship was too massive and too radioactive to lift off from our planet safely. Total mass at departure would be 54,000 tons. That is roughly the weight of a modern aircraft carrier. Of that mass, 50,000 tons would be fuel. The actual payload, the scientific instruments and probes, accounted for only 450 tons. The rest was structure, engines and shielding. The fuel was the engineering heart of the design. Daedalus would burn tiny pellets of deuterium and helium-3, a rare isotope of helium with 2 protons and 1 neutron. Each pellet would be the size of a small marble. The ship would fire electron beams at the pellet, compressing it so violently that the atoms inside would fuse together, releasing a burst of energy in the process. This is inertial confinement fusion. The pellets would ignite at a rate of 250 per second, producing a continuous stream of plasma jets out the back of the engine. The numbers on this engine are almost unbelievable. The exhaust would leave the ship at roughly 6 million miles per hour, thousands of times faster than any chemical rocket. Daedalus could sustain this burn for 2 years straight during the first stage. Then the first stage would separate, and a smaller second stage would continue burning for another 2 years. Top cruise velocity, 12% of light speed. Time to Barnard's star, the original target, approximately 50 years. Time to Proxima Centauri using the same design, about 36 years. For the first time in history, a serious engineering study had produced a starship design that could reach another star within a single human career. Not a lifetime, a career. A graduate student who joined the mission at 25 could live to receive the first data transmissions in retirement. Then the cost analysis arrived. The helium-3 fuel was the killer. Helium-3 is extremely rare on Earth. Our atmosphere contains almost none of it, because the light isotope escapes our gravity well over billions of years. The only accessible sources are the atmospheres of the gas giants. Daedalus would need 20,000 tons of helium-3. Extracting that much from Jupiter's atmosphere would require floating mining platforms, hundreds of them, operating for decades. The infrastructure alone would cost more than the entire space industry has ever spent combined. The team knew this. They included it in the report anyway. Daedalus was never meant to be built tomorrow. It was meant to prove that the design was physically possible, given sufficient industrial scale. That scale does not yet exist, and the fuel problem only gets worse from here. Helium-3 is the fuel that could carry us to the stars. It is also one of the rarest substances in our solar system, and harvesting it would demand an industrial effort larger than anything humanity has ever attempted. Here is what makes the isotope so valuable for Starship engines. When helium-3 fuses with deuterium, the reaction releases enormous energy, but it produces almost no neutrons. Neutrons are the bane of fusion reactors. They fly out in every direction, penetrate shielding, make metal radioactive, and destroy the structural integrity of engine components. A reactor that produces lots of neutrons has to be rebuilt constantly. A reactor that produces few neutrons can run for decades. Helium-3 fusion is the cleanest fuel cycle available. Every serious fusion starship design from Daedalus onward has assumed helium-3 as the primary propellant. The problem is finding enough of it. Earth's crust contains at best a few hundred kilograms of accessible helium-3 total across the entire planet. The isotope is created in certain radioactive decay chains, and it leaks out of nuclear weapons facilities, and that is essentially the global supply. Commercial price today runs about $45,000 per gram. At that price, fueling Daedalus would cost roughly $900 trillion, more than 10 times the total economic output of the entire human species for an entire year. The Moon offers slightly better prospects. Over billions of years, the solar wind has deposited helium-3 into the lunar soil. Every square meter of the surface, down to a depth of several meters, contains trace amounts of the isotope. Estimates suggest the Moon holds roughly 1 million tons of helium-3 scattered across its dusty face. Mining thus would require scraping the entire lunar surface, baking the regolith at high temperatures, and capturing the gases released. You would need to process billions of tons of soil to extract each ton of helium-3. The concentration is that low. A fleet of autonomous mining rovers, solar-powered processing plants, and orbital transport craft would need to operate continuously for decades. The infrastructure alone would dwarf anything humans have built off-planet. And even all of that would not be enough. Daedalus needed 20,000 tons of helium-3. Icarus, the British Interplanetary Society's follow-up project started in 2009, trimmed that down to about 8,000 tons, still enormous. The Moon's accessible reserves might cover a handful of missions before running dry. Which leaves the gas giants. Jupiter's atmosphere contains helium-3 in significant quantities, diluted across an unthinkable volume of hydrogen and other gases. Saturn, Uranus, and Neptune carry similar loads. To extract it, engineers have proposed floating atmospheric scoops. These would be aerodynamic craft, fusion-powered themselves, that would skim the upper atmospheres of the gas giants at enormous speeds, filtering out helium-3 one molecule at a time. The engineering challenges stack quickly. Jupiter's atmosphere is a hostile environment. Winds exceed 300 miles per hour. Pressure changes crush metal. Radiation from the planet's magnetic field would kill any unshielded electronics within hours. A scoop craft would need to be built from materials we do not yet manufacture, powered by reactors we do not yet operate, navigated by software we have not yet written. The fuel problem is not a minor obstacle. It is a civilizational investment. A full interstellar program would require a fully industrialized solar system first. The star comes after the gas giants, not before. 2009. 31 years after Daedalus was published, a new group of engineers decided to revisit the design. The name they chose was Icarus, after the mythical son of Daedalus who flew too close to the light and fell. The name was a warning to themselves. Stay humble, check the math. The original project had assumptions baked into it that 3 decades of new physics might overturn. The Icarus team was international. Members from the British Interplanetary Society, the Tau Zero Foundation, and a loose network of aerospace engineers and plasma physicists volunteered their time. The goal was not to build the ship. The goal was to update the design using modern knowledge, modern materials, and modern mission planning. The updates were brutal. Daedalus, as originally conceived, had several engineering flaws that the 70s team either missed or dismissed. The fuel pellet ignition system, for example, relied on electron beams converging on a target the size of a marble with near-perfect timing. The Icarus team ran the numbers using modern inertial confinement fusion research. The original Daedalus pellet design would not have ignited. The compression was insufficient. The ship, as drawn, would have been a beautiful metal tube full of inert fuel, coasting at Voyager speeds, fixable. The Icarus redesign added stronger laser drivers and better pellet geometry. The new pellets were smaller, denser, and wrapped in a heavy metal shell that would absorb the laser energy and implode the fuel from all sides at once. Laboratory experiments at the National Ignition Facility in California, which began achieving controlled fusion ignition in 2022, validated parts of the design. Another fix involved the engine bell. Daedalus proposed a magnetic nozzle, a set of superconducting coils that would shape the fusion plasma into a directed jet. The 70s team assumed the coils could survive the radiation environment. The Icarus team ran updated models and concluded the coils would melt within weeks of continuous operation. New materials and a redesigned cooling system were added to the blueprint. The helium-3 supply problem remained unsolved. Icarus reduced the fuel requirements significantly, down to about 8,000 tons instead of 20,000. That is better. It is not survivable. The mining infrastructure required to produce 8,000 tons of helium-3 is still an infrastructure that does not exist and may never exist. Icarus also tackled a question Daedalus deliberately ignored: deceleration. The original Daedalus was a flyby mission. The ship would scream past its target at 12% of light speed, take pictures for a few hours, and keep going forever into deep space. No brakes, no orbit, a single pass, and a lifetime of silence. Icarus proposed adding a third stage specifically for deceleration. That stage would need almost as much fuel as the first two combined. The total mass at departure ballooned to over 100,000 tons. The ship became the single largest object humans had ever designed, by an enormous margin. Deceleration, it turns out, doubles every problem, and it is not optional for any mission that wants to actually study what it finds. A flyby at 12% of light speed gives you about 4 hours of close observation. After that, the target shrinks into the distance forever. That constraint haunts every interstellar concept, but it is not the constraint that killed Orion outright. That one came from Geneva. October 1963. Moscow. The United States, the Soviet Union, and the United Kingdom signed a document that would end Project Orion's future before the first nuclear pulse drive had ever been built. The Partial Nuclear Test Ban Treaty. On paper, it was a simple agreement: no nuclear detonations in the atmosphere, no nuclear detonations underwater, no nuclear detonations in outer space. The treaty was a response to public fear about fallout. Radioactive isotopes from above-ground weapons tests had been detected in milk, in bones, in the teeth of children born during the testing era. The signatories wanted the tests driven underground, where the fallout could be contained. Nobody in the negotiating rooms was thinking about starships. But Orion was a starship that required nuclear detonations in outer space. Thousands of them. A single interplanetary mission to Mars would involve roughly 1,000 bomb pulses. An interstellar mission to Proxima Centauri would involve perhaps 1 million. Each detonation would release radioactive debris, some of which would escape the propulsion plume and spread into space. Some would fall back into Earth's atmosphere if the ship launched from the ground. The treaty language was clear. Orion was illegal under international law. The project continued for 2 more years at low funding, mostly on paper, while the legal team argued about interpretation. The United States Air Force, which had taken over Orion funding from the original civilian team, eventually abandoned the program in 1965. The files went into storage. The pusher plate design stopped evolving. Freeman Dyson, who had spent years working on Orion, wrote later that the treaty signing was the end of a certain kind of dream. He described the moment with a mix of grief and relief. Grief for the ship that would not fly. Relief because he, more than most, understood what Orion launches would release into the upper atmosphere. The fallout estimates from his own calculations suggested that a single ground launch would cause several hundred statistical cancer deaths worldwide. A sustained launch program might cause tens of thousands. The treaty addressed the moral problem by closing the physical one. No more bombs in the air. No more starships powered by bombs. Simple. There is a cruel irony here. Orion was the only interstellar propulsion system ever designed that required no new physics. The fuel existed. The bombs existed. The engineering was hard but not speculative. Every other starship concept on the table, from Daedalus to Starshot, requires technologies that do not yet work at the scale required. Orion could, in principle, be built today with components that already sit in military warehouses. It just would not be legal, and the political calculation that made it illegal was not wrong. The world that signed the Test Ban Treaty was terrified of a nuclear future. They had watched Castle Bravo scatter radioactive ash across the Pacific in 1954. They had seen Japanese fishermen die from fallout exposure. Opening space to nuclear weapons, even for peaceful purposes, felt like a door that could not be unclosed. So the dream of riding atomic bombs to the stars was traded for safety at home. A reasonable trade. But it meant the next interstellar concepts had to work within legal, political, and environmental limits Orion never acknowledged. The designers had to get creative. One of the strangest solutions involved leaving the engine behind entirely. 2016, Silicon Valley. Russian-Israeli billionaire Yuri Milner stood on a stage beside Stephen Hawking and announced a $100 million initiative called Breakthrough Starshot. The plan was the most radical interstellar proposal in history, and in some ways the most conservative. Milner was offering a different answer to the Starship question. What if the Starship did not carry its own fuel at all? The design called for a spacecraft smaller than a postage stamp, a silicon chip a few centimeters across, loaded with cameras, sensors, and a tiny laser communicator. Attached to the chip would be a sail made of ultra-thin reflective material, roughly 10 feet across, weighing less than a gram. The entire package, chip plus sail, would mass just a few grams. Engineers called it a star chip. The fuel problem was solved by leaving the fuel on Earth. A ground-based laser array, 100 gigawatts of coherent light, would aim at the sail and fire for approximately 10 minutes. Photons from the laser would bounce off the sail, transferring momentum with each reflection. The star chip would accelerate at roughly 10,000 times the force of Earth's gravity. By the end of the 10-minute burn, the probe would be moving at 20% of the speed of light. 20%. 134 million miles per hour. 4,000 times faster than Voyager. At that speed, the trip to Proxima Centauri would take about 20 years. A graduate student who helped launch the mission could receive the first data transmissions before retirement. The data itself, travelling back at light speed, would take another 4 years to arrive. But the total mission timeline from launch to first images of Proxima Centauri B would fit inside a single career. The design had real scientific pedigree. The lead author of the core physics paper was Philip Lubin, a physicist at the University of California, Santa Barbara. Lubin had spent years researching directed energy propulsion, originally in the context of planetary defense against asteroids. His calculations showed that a sufficiently powerful laser array could, in principle, push a gram-scale payload to relativistic speeds within a few minutes. The payload would be tiny, that was the key. Chemical rockets fail at interstellar distances because the fuel-to-payload ratio becomes impossible. Starshot flipped the problem. If the payload weighs almost nothing, the fuel mass stays on the ground, where you can scale it up as much as you need. The rocket equation stops applying. The only limits are the laser technology, the sail materials, and the precision of the aim. All three of those limits are severe. The laser array required for Starshot does not exist. The strongest continuous laser humans have built operates at roughly 1 megawatt. Starshot needs 100 gigawatts. That is 100,000 times more power, and the laser must be phased, meaning thousands of individual emitters must fire in perfect synchronization, their beams combining into a single coherent column of light, aimed at a target moving away at relativistic speed. The sail is just as hard. It must survive temperatures that would vaporize steel, reflect almost 100% of the incoming laser light, and remain structurally stable under acceleration forces that would crush a human body into paste. Milner's $100 million was seed money. The real cost estimates for building Starshot infrastructure run into the tens of billions, and in 2025, Scientific American reported that the project had gone quiet. A 100 gigawatt laser. That is the power requirement for Breakthrough Starshot. To feel what that number means, consider the following comparison. The entire electrical power consumption of France, averaged across a day, is about 60 gigawatts. Starshot's laser would need to exceed the continuous power draw of an advanced industrial nation, concentrated into a single beam, aimed at a target the size of a dinner plate moving away from Earth at 2/10 the speed of light. The laser cannot be a single emitter. No laser that powerful has ever been built or seriously proposed. Materials cannot handle the heat. Cooling systems cannot remove the thermal load fast enough. Optics cannot focus the beam without melting. A single 100 gigawatt laser would, essentially, flash vaporize itself the moment it switched on. The solution is called a phased array. Thousands of smaller lasers, each rated at around 100 kilowatts, aimed at a common target. Their beams must combine in the atmosphere above the array to produce a single coherent column of light, with the total power of all the contributors. Phased arrays exist today, mostly in radar systems, but at nothing close to Starshot's required scale. The engineering precision is staggering. Every emitter in the array must fire at exactly the same frequency. The phase of every wave must be aligned to within a fraction of a wavelength. Atmospheric turbulence, which bends and scatters light in unpredictable ways, must be corrected in real time. The entire array must track a target accelerating at 10,000 times Earth gravity, maintaining focus on a sail that is, by the end of the 10-minute burn, 4 million miles away. The array itself would cover roughly 1 square mile of ground. Thousands of individual laser modules, each connected to a power grid capable of delivering sustained multi-gigawatt output. The cooling system alone, to prevent the lasers from melting their own mounts, would require a small river's worth of water flow. Most proposed locations are high-altitude desert sites, where atmospheric interference is lowest. Chile's Atacama region is a leading candidate. So is the Tibetan Plateau. Cost estimates for the laser array range widely. Philip Lubin's original paper suggested a few $1 billion for a scaled-down prototype. Independent engineering reviews, including assessments by aerospace consultancies, place the realistic cost closer to $50 to $100 billion for the full system. That is roughly the annual budget of NASA 10 times over. No single nation has shown willingness to fund such a project. Private investment has stalled. There is also the diplomatic problem. A 100 gigawatt laser aimed at the sky is indistinguishable from a weapon. Any nation that builds one will face accusations of constructing an anti-satellite system, or worse, an orbital strike platform. The physics do not care about the intended target. A laser that can push a gram of silicon to relativistic speed can also vaporize a reconnaissance satellite in low Earth orbit. International treaties would need to be negotiated before construction began, and those treaties do not yet exist. And assuming all of these problems are solved, assuming the funding appears, the treaties are signed, the emitters are built, and the power grid is connected, the laser still only works if the sail survives the burn. The sail is the next impossibility. Breakthrough Starshot's engineers faced a specific ugly question early in the design process. What happens when a single starship fails mid-flight? The answer is nothing. The mission ends. The probe drifts, inert, into deep space, carrying its cameras and sensors and tiny laser communicator silent into the void. 4 years of light-speed transmission lag mean that ground controllers would not even know about the failure for a long time. By the time the bad news arrived, the probe would be thousands of times farther away than any rescue mission could reach. This is not a hypothetical risk. The failure rate for interstellar probes, based on current estimates, is roughly 50% per mission, possibly higher. Dust impacts, cosmic ray damage, software errors, component decay, solar radiation during the Earth orbit acceleration phase, beam targeting errors during the laser burn. Any one of these can kill a gram-scale spacecraft that has no redundant systems, no backup computer, and no repair capability, so Starshot's planners made a hard decision. Do not launch one probe, launch 1,000. The math works like this. If each probe has a 50% chance of survival, launching 2 probes gives you a 75% chance that at least one arrives. 10 probes, almost certain success. 1,000 probes, you can afford to lose 999 and still get data from the survivor. The swarm strategy converts a coin flip mission into a near guaranteed one. The challenge is that launching 1,000 probes means firing the 100 gigawatt laser 1,000 times. Each burn lasts 10 minutes. Each burn requires full atmospheric compensation, perfect pointing accuracy, and flawless phase coherence. The total operational time of the laser array, just to launch the swarm, runs into tens of thousands of hours. That is years of continuous operation, and between each shot the laser must cool down, recalibrate, and reacquire the next target probe in low Earth orbit. The probes themselves need to be mass-produced. 1,000 starships, each a complete interstellar spacecraft, each tested and flight qualified, each fitted with its own sail. The manufacturing run would dwarf any spacecraft production in history. Modern aerospace companies build perhaps a handful of interplanetary probes per decade. Starshot would need to build 1,000 in a few years. There is an upside. At gram scale, the cost per probe drops dramatically. Each Starship would probably cost somewhere in the range of a few $1,000s to manufacture, not including the sale. The total probe inventory, minus launch infrastructure, might cost less than a single conventional Mars rover. Then there is the data problem. 1,000 probes approaching Proxima Centauri at 20% of light speed will arrive, spread across weeks, due to slight differences in their acceleration profiles. Each one will send back a trickle of data using its gram-scale laser transmitter. The signals will be extraordinarily faint. Earth's receiving equipment will need to distinguish one probe's transmission from another and from background noise across a 4 light-year gap. The swarm approach is elegant. It is also an admission of fragility. Every interstellar spacecraft built at gram scale will face the same odds, and the only way to beat those odds is redundancy at enormous scale. The question of what might kill each individual probe is worth examining in detail, because the interstellar medium, once thought nearly empty, is full of threats. Interstellar space is not empty. This is the first thing every starship designer has to accept. The vast darkness between our star and Proxima Centauri contains, on average, about 1 atom of hydrogen per cubic centimetre. Dust grains ranging from specks too small to see up to the size of a sand grain drift through the medium at densities of roughly 1 particle per several hundred cubic meters. At Voyager speeds, these particles are harmless. A hydrogen atom bumping into a probe moving at 38,000 miles per hour transfers almost no energy. The probe does not notice. The atom bounces off. At 20% of light speed, everything changes. Kinetic energy scales with the square of velocity. Double the speed, 4 times the energy, 10 times the speed, 100 times the energy. Breakthrough Starshot probes would move at roughly 4,000 times Voyager's speed, which means each particle impact would deliver 16 billion times more energy. A hydrogen atom that bounces harmlessly off Voyager becomes, at relativistic speed, a kinetic weapon. A dust grain of a few micrometers across, striking a starship head-on at 20% of light speed, would release the energy equivalent of a small explosive. The impact would punch clean through the probe. The silicon chip would shatter, the sail would tear, the mission would end in a single flash. Even individual atoms become a problem. At relativistic speed, a stream of hydrogen atoms acts less like a gas and more like a continuous particle beam. Each atom strikes with enough energy to ionize the surface of the probe, strip electrons from atoms in the hull, and slowly erode the outer layer of any structure it hits. Over a 20-year journey, the cumulative damage adds up. Cameras degrade, sensors go blind, chips become unreliable. A study published in 2016 by astrophysicist Thiem Hoang and colleagues at the University of Toronto examined the dust problem in detail. Their conclusion was mixed. Large dust grains, the kind that could destroy a probe in a single hit, are rare enough that most starships in a swarm would probably avoid them. But smaller particles, below about 1/10 of a micrometer across, are common enough that every probe would experience significant surface erosion during the journey. The Hoang team proposed several mitigations. The probe could be oriented edge-on to the direction of flight, presenting the smallest possible cross-section to incoming particles. A thin shield of beryllium or graphite placed in front of the probe could absorb the worst impacts before they reached the sensors. The sail itself, once the laser acceleration phase ended, could be folded or jettisoned to reduce target area. These mitigations help. They do not eliminate the risk. A large enough dust grain encountered anywhere along the 4 light-year path will destroy any probe it hits. There is no shield thin enough to stop it and light enough to accelerate to relativistic speed. This is another reason for the swarm strategy. Some probes will die. The survivors will finish the mission. Dust is not the only threat in the interstellar medium. The hydrogen gas itself moving past a relativistic probe looks less like empty space and more like a hard wind of radiation. The ionizing effect on electronics is severe, persistent, and cumulative, and dust is only the first of the particle problems a starship must survive. Beyond the dust, another invisible threat fills every cubic inch of interstellar space: cosmic rays. These are high-energy particles, mostly protons, accelerated to near light speed by distant supernovae, active galactic nuclei, and other violent events scattered across the Milky Way. They slam into the solar system from every direction. Earth's magnetic field deflects most of them. Once you leave that protection, cosmic rays become a constant rain of ionizing radiation. For a starship, cosmic rays are not a survival problem in the traditional sense. The probes are not alive. The hardware does not die from radiation sickness. But cosmic rays do something almost as bad. They scramble electronics. Here is what happens at the silicon level. A cosmic ray proton moving at 99% of light speed plows through a semiconductor chip. As it passes, it ionizes a track of atoms, knocking electrons loose. If the track crosses a transistor in the middle of a computation, the transistor's state can flip. A 0 becomes a 1 becomes a 0. The computer suddenly is holding the wrong number. Engineers call this a single event upset. It is the cause of mysterious computer glitches on every spacecraft ever flown beyond Earth orbit. Mars rovers experience hundreds of them per year. The Juno spacecraft at Jupiter has lost instruments temporarily to cosmic ray hits. The International Space Station's computers reboot occasionally from upsets that no amount of shielding can fully prevent. For an interstellar probe, the problem is worse. The probe must operate autonomously for 20 to 50 years without ground support. Every command takes years to reach it. Every error the hardware makes must be caught and corrected by the probe itself. A single event upset that corrupts a critical memory register or flips a bit in the probe's navigation software could end the mission silently. The probe would keep flying. It would just fly in the wrong direction, or stop taking pictures, or forget how to transmit. Shielding helps, but only against the lower energy particles. The most energetic cosmic rays punch through any shield light enough to fly. Adding more shielding adds mass, which breaks the rocket equation. Every gram of lead wrapped around a starship's computer is a gram the laser has to push to 20% of light speed, which increases the laser power requirement, which was already pushing the edge of physical possibility. Modern aerospace chips use a technique called radiation hardening. The transistors are built with redundant structures. Every bit of memory is stored 3 times, with voting logic that picks the majority value when the 3 copies disagree. Single event upsets still happen. The hardening catches most of them before they cause mission failure. Radiation-hardened chips are expensive. They are also slower, bulkier, and more power-hungry than commercial silicon. A starship designed with full radiation hardening would weigh several grams instead of fractions of a gram. That mass difference matters when you are trying to push the probe with a laser. The 20-year journey to Proxima Centauri will expose each probe to roughly the lifetime cosmic ray dose of a spacecraft in Jupiter's magnetic field times 20. The cumulative damage is significant. Most probes will experience some hardware degradation by arrival. Some will experience catastrophic failure. This is another reason the swarm must be large. Redundancy is the only defense against a threat that cannot be fully blocked. And even the probes that survive the flight face one last challenge on arrival. They must send the data home. A starship at Proxima Centauri takes a picture. The picture is compressed, encoded, and fed into a small laser transmitter built into the probe structure. The transmitter fires a beam of coherent light back toward Earth. The signal travels for 4 years and 3 months, crossing 25 trillion miles of interstellar vacuum before it reaches our receiving equipment. By the time the signal arrives at Earth, it is almost gone. The physics of interstellar communication are brutal. A laser beam, no matter how tightly focused, spreads as it travels. The beam from a gram-scale transmitter, even using the best optics that can fit on a postage stamp-sized probe, will have spread to cover roughly the entire orbit of Earth by the time it reaches our planet. The energy density arriving at any particular spot in Earth's orbit is fantastically small, picowatts, femtowatts, a signal so faint that detecting it against the background noise of the cosmos is an engineering feat unto itself. The breakthrough Starshot team has an answer, at least on paper. The same phased laser array that accelerates the probes can, in principle, operate as a giant receiver. Billions of individual photodetectors spread across 1 square mile of desert collect the incoming photons and combine their signals through phase-sensitive electronics. The array becomes, effectively, the largest optical telescope ever built, tuned to the exact wavelength the probes are transmitting. Even with the array acting as a receiver, the data rate will be small. Estimates from the breakthrough Starshot team suggest perhaps a few bits per second at best. A single photograph from a starship might take hours or days to transmit fully. The 20-megapixel cameras the team hopes to build would need to prioritize ruthlessly. Send a low-resolution preview first. Send high-resolution images only of the most interesting features. Discard everything else. The aim is another problem. The probe must know, at the moment of transmission, where Earth will be when the signal arrives, 4 years and 3 months in the future. Our planet moves around the host star at roughly 67,000 miles per hour. During the signal's travel time, Earth will cover over 2 billion miles of orbital path. The probe must calculate Earth's future position with extraordinary precision and aim its transmitter at that predicted point, not at the point Earth occupies at the moment of sending. Miss by a fraction of a degree, and the beam sweeps past Earth's orbit entirely. The data is lost to deep space, forever. Then there is the question of what to send. A probe arriving at Proxima Centauri has, at most, a few hours of useful observation time during its high-speed flyby. The probe will cross the entire planetary system of Proxima Centauri in less than an hour. All the pictures, all the magnetometer readings, all the particle measurements must be collected during that brief pass and stored in onboard memory. Then the probe spends the next 4 years on the far side of the star system, transmitting the data slowly back to Earth while drifting into empty space. Some of the data will arrive. Some will be corrupted by interstellar scintillation, the twinkling effect that degrades signals passing through turbulent gas between stars. Some will be lost to cosmic ray hits on the onboard storage. The image that eventually appears on a screen at mission control will be a reconstruction, pieced together from fragments, partial and imperfect. And arriving is just half the mission. What comes next depends entirely on whether the probe can stop. Communication at interstellar distances creates a problem that has no analogue in any other kind of exploration humans have ever attempted. The speed of light. Light, the fastest thing in the universe, takes 4 years and 3 months to travel from Proxima Centauri to Earth. That is a hard limit. No information, no signal, no command, no data packet can cross the gap faster. It is a rule baked into the fundamental structure of reality, and no engineering trick will ever loosen it. Here is what this means for a real mission. Imagine a starship arrives at Proxima Centauri on a Tuesday. The probe takes its photographs. It transmits the data. The signal leaves the probe at the moment of transmission. Over 4 years pass. On Earth, engineers are still running the rest of their lives. They are marrying, having children, retiring, dying. In 2038, assuming a launch in 2028 and a 20-year flight, the first photons of data arrive at the receiving array. Mission controllers discover that their probe has reached its target. The discovery is 4 years old by the time they learn about it. If a problem occurred during the probe's approach, something the engineers on Earth might have been able to solve with a remote command, the window to act was gone before anyone knew the problem existed. A correction beam sent from Earth in response to the new data would take another 4 years to reach the probe's location. 8 years round trip. By then, the probe has moved another 12 billion miles past its closest approach, receding into deep space on its post-flyby trajectory. There is nothing to correct. The probe is already gone. This is called the light speed delay, and it changes the entire nature of mission control. Conventional spacecraft, even at Mars, can be commanded in near real time. A rover on Mars has a round-trip communication delay of up to 40 minutes. Slow, but manageable. Engineers can send a command and wait for a response during a single working day. At Proxima Centauri, there is no real-time control. There cannot be. The probe must make every decision by itself. Every navigation adjustment, every exposure setting, every transmission timing must be planned in advance and programmed into the probe's software before launch. The probe is effectively on its own from the moment the laser shuts off. This places extraordinary demands on the onboard software. Code written 20 years before the probe reaches Proxima Centauri must execute flawlessly across a range of conditions the programmers cannot fully predict. The software must handle hardware failures, unexpected dust impacts, radiation-induced memory errors, and any surprises the Proxima Centauri system throws at the probe during its brief flyby, all without any possibility of a bug fix, a patch, or a clever human workaround. Spacecraft software has failed in the past over much shorter distances. The Mars Polar Lander crashed in 1999 because of a software error that confused metric and imperial units. The Hubble Space Telescope was launched in 1990 with an optical flaw caused by a software-driven manufacturing mistake. These errors were caught eventually because there were humans close enough to fix them. At Proxima Centauri there will be no second chance. A bug that slips into the final code becomes a silent, unfixable mission failure, and the light speed delay is only the beginning of the arrival problem. There is a worse one: stopping. Every Starship concept published so far has a dirty secret. Most of them are flyby missions. They reach the target star, they scream past at a significant fraction of light speed, and they keep going. They never slow down. They never enter orbit. They never stop. The reason is simple. Stopping is harder than going. Here is the physics. To accelerate a probe from rest to 20% of light speed, you need a certain amount of energy. To decelerate the same probe from 20% of light speed back to zero, you need exactly the same amount of energy. There is no free coasting down. There is no atmospheric break at an alien star. The only way to slow the probe is to push it backward with some force, matching the forward momentum the launch laser originally gave it. For breakthrough Starshot, the deceleration problem is essentially unsolved. The probes are gram scale. They carry no fuel. They have no rockets. The laser that accelerated them is 4 light-years away, and even if it were close enough to fire, the probes are moving away from it at 20% of light speed. A braking beam fired from Earth would take over 4 years to reach the probe, by which time the probe would be deep into the Proxima Centauri system, or already past it. Some theorists have proposed using Proxima Centauri's own starlight as a braking force. The probe flips its sail around at some point during the approach, using the star's radiation pressure to slow down. The math, unfortunately, does not close. Proxima Centauri is a red dwarf, a dim star with far less radiation output than our own. Its stellar wind would decelerate a light sail, but only barely, and only over distances much larger than the approach geometry allows. A 20-year flight followed by 2 centuries of slow deceleration gets you into orbit. Nobody wants a 200-year braking phase. Other proposals involve magnetic sails. A large loop of superconducting wire deployed by the probe during approach generates a magnetic field that interacts with the interstellar plasma. The plasma pushes back on the magnetic field, slowing the probe down. In theory, this works. In practice, the probe would need to carry a superconductor loop thousands of miles across, along with the cooling system needed to keep it at cryogenic temperatures for the entire flight. Not going to fit inside a gram-scale star chip. For larger ships like Daedalus or Icarus, the deceleration problem is addressed with additional fuel stages. These ships carry enough propellant to decelerate at the target. Icarus, in its updated design, devotes roughly 1/3 of its total mass to the braking stage. That is thousands of tons of deuterium and helium-3 carried across 4 light-years solely to bring the ship to rest at the destination. The fuel penalty is enormous. It is also unavoidable. A science mission that does not stop cannot study the target in any detail. A few hours of flyby data is not worth the centuries of investment required to send the ship. So there are 2 Starship categories: fast, cheap, one-way flybys with brief observation windows, slow, expensive, fully decelerating missions with years of observation but centuries of travel. Neither version is possible with today's technology, Both require infrastructure and fuel production that humanity has not yet begun to build. Past the deceleration problem lies an even more speculative frontier, one where the spacecraft does not just slow down, it brakes using magnetism itself. 1788. A Dutch physicist named Johann Hendrik van der Waals worked out the equations governing how charged particles respond to magnetic fields. 2 centuries later, a NASA physicist named Robert Zubrin used those equations to propose one of the strangest Starship braking systems ever sketched on paper, the magnetic sail, or magsail, as its designers prefer to call it. The concept begins with a simple fact about the interstellar medium. Space between stars is not empty. It contains a thin plasma of charged particles, mostly protons and electrons, drifting at low speeds relative to the galaxy. At interstellar cruising speed, a starship plows through this plasma at enormous velocity. From the ship's perspective, the medium rushes toward it at a significant fraction of light speed, acting like a soft wind of electrically charged debris. A magnetic field can deflect charged particles. Every physicist knows this. Earth's magnetic field deflects cosmic rays. The magsail idea takes that principle and turns it into a brake. The ship deploys a loop of superconducting wire, unfurled from a compact storage reel as the probe approaches its target star. The loop carries a massive electric current, which generates a magnetic field extending for hundreds or thousands of miles in every direction. Protons in the incoming plasma feel the field, curve in their paths, and transfer momentum to the loop as they are deflected. The ship slows down, not quickly, not efficiently, but continuously for years with no fuel consumed. The engineering requirements are punishing. The superconducting loop must be enormous. Early designs called for a wire loop roughly 60 miles in diameter. The wire itself must remain at cryogenic temperatures throughout the flight, which means a cooling system that can survive for decades in deep space. Superconductors lose their properties if they warm up. A single failure in the cooling system, a single micrometeorite hit on a critical component, and the loop becomes a regular wire. The current collapses, the brake stops working, the deceleration is slow. A magsail-equipped starship travelling at 10% of light speed might take 30 to 50 years to come to rest at the destination. That adds decades onto the mission timeline. A voyage that was 50 years outbound becomes 80 or 90 years total, counting the braking phase. Human crews aging on the ship would spend much of their lives just decelerating. For a gram-scale probe like a starship, the magsail is essentially impossible. The loop mass alone dwarfs the probe. Scaling the concept down to fit on a postage stamp produces a brake so weak it would take centuries to meaningfully slow the craft. The magsail is a technology for large ships, not tiny ones. There are other wrinkles. The interstellar plasma is not uniform. Denser regions would decelerate the ship faster. Thinner regions would decelerate it slower. Navigating the approach requires accurate maps of the plasma density along the final approach path, maps that do not exist and cannot be made from Earth. The ship would have to measure the plasma itself in real time and adjust its deceleration profile accordingly. Another autonomous system that must work flawlessly over decades. Magnetic sails remain an active area of research. Teams at NASA Glenn Research Center and at several European universities continue to publish papers on the concept. The math is sound, the engineering is distant. No magsail has ever been tested in space, not even a small one. And even magsails are conservative compared to what comes next. On the energy ladder, antimatter sits at the top rung, nothing physical exceeds it. When a gram of antimatter meets a gram of ordinary matter, the pair annihilates completely, converting all of their combined mass into energy. Every atom, every proton, every electron vanishes in a flash that produces the full equivalent of mass energy conversion. The yield is staggering. 1 gram of antimatter plus 1 gram of matter releases about 90 trillion joules of energy. That is roughly the explosive yield of 43 kilotons of TNT, twice the bomb dropped on Hiroshima, from 2 grams of fuel. For a Starship designer, antimatter is the dream fuel. A small quantity, properly harnessed, could accelerate a large ship to a significant fraction of a light speed. Penn State physicist Gerald Smith, working with NASA researchers in the 1990s and early 2000s, calculated that a probe massing about 100 tons could reach Proxima Centauri in 40 years using just a few milligrams of antihydrogen as a trigger for a larger fusion drive. The ship would be fast, compact, and capable of deceleration at the target. The fuel supply problem, however, is catastrophic. Antimatter does not exist naturally in the universe in accessible quantities. Every atom in our solar system, every molecule on Earth, every particle in our bodies is ordinary matter. Antimatter must be manufactured, 1 particle at a time, in specialized accelerator facilities. The largest antimatter factory currently operating is the antiproton decelerator at the European Organization for Nuclear Research, known as CERN, near Geneva. CERN produces, on its best days, roughly 10 nanograms of antimatter per year, that is 10 billionths of a gram. The facility runs continuously, consuming enormous amounts of electricity, operated by hundreds of physicists and engineers. A full year of production yields less antimatter than fits on a grain of sand. A starship would need grams, maybe kilograms. To produce a single gram of antimatter at CERN's current rate would take about 100 million years. The total antimatter ever produced by all human experiments, added up across every particle physics laboratory in history, comes to less than 1 billionth of a gram. Scaling antimatter production to Starship quantities would require building thousands of dedicated factories, each consuming the electricity output of a small nation. The cost estimates are impossible. Some analyses suggest a gram of antimatter produced at industrial scale would cost roughly $25 billion. A kilogram would cost $25 trillion, far more than the total economic output of every nation on Earth combined. Then there is the storage problem. Antimatter annihilates the instant it touches ordinary matter. You cannot store it in a tank. You cannot pump it through a pipe. The only way to contain antimatter is inside a magnetic trap, where the charged antiparticles are held suspended in vacuum by electromagnetic fields. Current traps hold a handful of antiprotons at a time. Scaling to gram-level storage would require cryogenic magnetic containment on a scale humans have never built. A single power failure in the containment system, even for a fraction of a second, releases all the stored antimatter into contact with the trap walls. The resulting explosion destroys the factory or the ship, depending on where the storage is located. Antimatter is the most dangerous substance humans have ever handled, and the quantities required for Starship propulsion would dwarf every laboratory sample ever produced. The dream fuel is real. The dream is not reachable, not with current civilization, not soon. Before laser sails, there were solar sails. The idea that sunlight itself could push a spacecraft across interplanetary space goes back more than a century. Konstantin Tsiolkovsky, the Russian rocketry pioneer, proposed it in the 1920s. Friedrich Zander, another Soviet scientist, refined the concept in 1924. Both men saw the same physics, Photons carry momentum. A reflective sheet in the path of sunlight gets pushed by the light, just as a boat sail gets pushed by the wind. Solar sails are real. They work. The Japanese Space Agency launched a successful solar sail called Icarus in 2010, which sailed to Venus under sunlight pressure alone. The Planetary Society, a private group, launched LightSail 2 in 2019, which successfully raised its orbit around Earth using only photon pressure from our star. The technology is proven at interplanetary scales. The question is whether solar sails can reach another star, and the answer is no, not on their own. The problem is the inverse square law. Sunlight spreads out from our star in all directions. Double the distance from the star, and the light intensity drops by a factor of 4. Triple the distance, and it drops by a factor of 9. By the time a spacecraft reaches the orbit of Jupiter, the sunlight pressure available for propulsion is roughly 25 times weaker than near Earth. At Saturn, 80 times weaker. At Pluto, over 1,000 times weaker. Solar sails accelerate quickly in the inner system and then coast. Without another source of photon pressure, they cannot keep adding speed. Once they pass the orbit of Mars or so, the push becomes negligible. The sail drifts at whatever velocity it achieved during its brief acceleration phase, which is modest. A well-designed solar sail might reach a few 100,000 miles per hour. Roughly 10 times Voyager, still 1,500 times too slow to reach Proxima Centauri in a human lifetime. Some clever mission profiles can wring more performance out of a solar sail. The trick is to dive close to the host star first. A sail that swings past our star at a distance of a few million miles receives an enormous pulse of light pressure, accelerating it outward at much higher speeds than a sail starting from Earth's orbit. This is called a solar flyby maneuver, or sometimes a sundiver trajectory. With a close enough approach, a sail could reach perhaps 1% of light speed. 1%. That means 420 years to Proxima Centauri. Better than Voyager. Still generational. Still slower than every serious proposal actually being pursued today. The sundiver maneuver has its own problems. The sail must survive temperatures that would vaporize most materials. Near-star approach means the sail experiences heat far hotter than an industrial furnace. The sail coating must reflect almost all incoming light and emit the rest as infrared radiation, cooling itself through radiative emission. Materials like graphene, aluminum, and specially coated polymers have been proposed. None of them have been tested at the conditions a sundiver mission would require. This is why breakthrough Starshot moved to lasers. Photon pressure from sunlight tops out at what sunlight can provide. Photon pressure from a 100 gigawatt laser applied directly to a sail in low Earth orbit can be millions of times stronger than natural sunlight. The laser lets you scale the thrust independently of solar physics. Solar sails cannot reach the stars. Lasers can. But there is one other photon-related concept that some physicists refuse to let go of: the ramjet. 1960. An American physicist named Robert Bussard published an idea so audacious it became the defining image of interstellar travel for an entire generation of science fiction writers: the interstellar ramjet. Bussard's concept was elegant. Space between stars is not truly empty. It contains a thin gas of hydrogen, about 1 atom per cubic centimetre on average. If a starship could scoop up that hydrogen as it flew, compress the gas, fuse it in an onboard reactor, and eject the fusion products as exhaust, the ship would never need to carry its own fuel. The fuel would be gathered from space itself, continuously, as the mission progressed. No tanks, no fuel mass penalty. The rocket equation would stop applying. The math looked beautiful in 1960. Run the numbers, and a Bussard ramjet could, in theory, accelerate indefinitely. Keep scooping hydrogen, keep fusing, keep ejecting. Reach 90% of light speed, reach 99%. At relativistic speeds, time dilation would allow the crew to cross entire galaxies within a single human lifetime, while millennia passed back home. The idea electrified physicists and science fiction authors alike. Paul Anderson wrote an entire novel called Tau Zero in 1970, built around a Bussard ramjet that accelerated beyond control. Larry Niven used ramjets in his known space series. Carl Sagan mentioned them in Cosmos. For decades, the ramjet felt like the answer. The only honest propulsion system that offered true interstellar flight on human timescales. Then the math was checked more carefully. The first problem was the scoop. Interstellar hydrogen density is 1 atom per cubic centimetre. To gather enough hydrogen for meaningful thrust, the ramjet's scoop would need to be enormous. Early estimates suggested a magnetic collection field extending thousands of miles in every direction. The field would funnel protons into the ship's intake, where they would be compressed and fused. Generating a magnetic field that large, and keeping it stable while travelling at relativistic speeds, turned out to require power inputs far exceeding anything the fusion reactor could produce. The ramjet consumed more energy running its own scoop than it gained from burning the collected fuel. The second problem was the fusion reaction itself. Bussard assumed proton-proton fusion, the same reaction that powers our host star. The problem is that proton-proton fusion in a star takes place over billions of years because the rate is extraordinarily slow. Our star fuses hydrogen because it has thousands of trillions of tons of plasma available, all reacting simultaneously in the core. A ramjet's onboard reactor would have, at most, a few kilograms of hydrogen in the fusion chamber at any given moment. The reaction rate is too slow to produce useful thrust. The third problem was drag. A magnetic scoop that collects protons also experiences resistance from those protons. At relativistic speeds, the scoop acts as a drag brake, slowing the ship down. A Polish physicist named Andrzej Wolszczan calculated in 1989 that the drag force exceeds the thrust force for most realistic designs. The ramjet would decelerate itself, not accelerate. More recent analyses, including work by physicist Robert Zubrin, have been even harsher. Under almost every realistic set of assumptions, the Bussard ramjet fails. The math does not close. Some variants of the concept survive. A hybrid design, using a small amount of onboard antimatter to trigger the fusion reactions, works slightly better. But the original Bussard vision, a starship that sails forever on the hydrogen of deep space, remains a fantasy. Elegant, influential, physically impossible. Which brings us to the other kind of starship, the kind that carries its crew for centuries. If you cannot build a fast starship, build a slow one, and send it with enough food, water, air, and people to survive the journey. Build a world inside a hull, a self-contained ecosystem that sustains itself for centuries as it drifts between stars. Launch the ship, and the passengers who arrive at Proxima Centauri will be the descendants, many generations removed, of the people who boarded on Earth. This is the generation ship, and it has been the default interstellar concept in science fiction since the 1940s. The physics is easier. A ship travelling at 1% of light speed, about 7 million miles per hour, could reach Proxima Centauri in roughly 400 years. That is a demanding but tractable propulsion target. Fusion rockets, or even advanced nuclear electric drives, could in principle reach that velocity given enough fuel and enough mass. The engineering problem is not the propulsion, it is the ship itself. A generation ship must be a closed ecosystem. Nothing can be wasted. Every molecule of water must be recycled. Every breath of air must be scrubbed of carbon dioxide, replenished with oxygen, and returned to the crew. Every gram of food must be grown on board, harvested, and regrown. The ship is a planet in miniature, sealed against vacuum, and it must function without failure for 400 years. Biosphere. 2. A large glass enclosure built in the Arizona desert in the late 1980s attempted to create a closed ecosystem on Earth. 8 people lived inside it for 2 years. The experiment failed in multiple ways. Oxygen levels dropped mysteriously, requiring emergency injections from outside. Crops failed. Insect populations collapsed. The crew fought bitterly among themselves. Biosphere 2 was a well-funded project with expert design and unlimited outside support, and it could not maintain stability for even 2 years. A generation ship must work for 200 times longer, with no outside support of any kind. The crew is another problem. Human populations have minimum sizes for genetic viability. Below a certain number of individuals, inbreeding and genetic drift reduce the gene pool's diversity to the point where disease resistance, fertility, and general health collapse within a few generations. Population geneticists estimate the minimum viable crew size at somewhere between 100 and 10,000 people, depending on which study you trust. Most recent analyses suggest several thousand is required for safety over 4 centuries. That means the ship must house several thousand humans, along with all the plants, animals, microbes, and equipment needed to keep them alive. The ship becomes a structure massing tens or hundreds of thousands of tons. It must be pressurized. It must have artificial gravity, probably through rotation. It must have radiation shielding thick enough to protect against cosmic rays across 4 centuries of exposure. The social challenges are unprecedented. The people who board the ship will never see another star up close. Their children will know only the interior of the ship. Their great-grandchildren will be asked to maintain the mission as their inheritance without having chosen it. By generation 12, the crew will have forgotten what Earth looks like. The entire project depends on cultural continuity across more than 10 generations of humans born into a metal tube drifting through space. No society on Earth has maintained continuity that long without massive external pressures and extensive external support. The generation ship must do it with neither. Every mutiny, every cult, every power struggle, every civil war that occurs on the ship is a potential mission-ending event. And over 400 years, the probability of all of them is near certainty. If you cannot survive the trip awake, sleep through it. That is the logic behind cryosleep. Freeze the crew at launch, thaw them at arrival, and the subjective travel time becomes 0. No generations, no closed ecosystem, no cultural drift. Just a ship full of frozen humans, drifting across the void, waking at the destination. The problem is that cryosleep does not work. Not for humans, not for any mammal. And the biology that makes it fail is stubbornly resistant to every approach engineers have tried. Here is what happens when you freeze a human. Water, which makes up about 60% of the human body, expands as it transitions from liquid to solid. The expansion is violent at the cellular level. Ice crystals form inside cells, slicing through membranes, rupturing organelles, destroying the delicate machinery of biology. By the time a human body is fully frozen, every cell is full of microscopic knives. Thawing does not repair the damage. The cells are already dead. Cryopreservation laboratories work around this problem for small samples. Individual cells, embryos, even small tissue fragments can be frozen using a process called vitrification. The water in the sample is replaced with a cryoprotectant chemical, a kind of biological antifreeze that prevents ice crystals from forming. The sample becomes a glass-like solid rather than ice. Vitrification works reliably for embryos and for some tissue grafts. It does not work for whole organisms. The cryoprotectant chemicals are toxic at high concentrations. To vitrify a human body, you would need to replace most of the water with cryoprotectant, at concentrations that would poison every cell. The tissue would freeze without ice damage, but it would die from chemical toxicity instead. The cryopreservation trade-off is unforgiving. You can avoid ice crystals, or you can avoid poisoning, but you cannot avoid both. Some animals survive freezing in nature. Wood frogs, certain turtles, and a few insects produce natural antifreezes and survive partial freezing by carefully controlling where ice forms in their bodies. The frogs allow extracellular water, the water outside cells, to freeze while keeping intracellular water liquid. The cells shrink and dehydrate during the freeze but do not die. Upon thawing, the water returns to the cells and normal function resumes. Humans do not have this adaptation. Our biology is fundamentally different from a frog's. Researchers have studied frog cryobiology for decades, hoping to transfer the mechanisms to mammals. No success so far. Mammalian cells lack the genetic machinery to tolerate extracellular freezing. An alternative approach is to induce suspended animation without freezing. Lower the metabolic rate to near zero, cool the body to just above the freezing point, and let biological processes slow to a crawl. Some animals, including certain bears and ground squirrels, do this naturally during hibernation. Human hibernation research is ongoing at several medical centres, mostly driven by interest in emergency trauma medicine. Early results are encouraging but limited. Researchers have induced short-term torpor in pigs, lowering their metabolism for hours at a time. Extending this to years with full recovery remains unattempted. For a starship with a 20 or 50-year flight, hibernation would need to work reliably across that entire duration. Every crew member must be kept at reduced metabolic rate with minimal tissue damage for the whole journey. No power failures, no medical emergencies the onboard systems cannot handle, no cases of metabolic drift that leave a crew member aged or dead at arrival. The biology is not ready. And microgravity during the long sleep brings another disaster. Astronauts returning from 6-month missions on the International Space Station have weaker bones than before they left. Specifically, they lose about 1 to 2% of their bone mineral density per month in microgravity. Over a typical rotation, the loss adds up to 10 or 15% of total skeletal mass. Bones from the lower spine, the hips, and the thighs are hit hardest. These are the weight-bearing bones on Earth, and in microgravity, the lack of load signals the body to dissolve them. The process is called spaceflight osteopenia, and no countermeasure has eliminated it. Astronauts on the space station exercise for 2 hours per day, every day, using resistance machines designed to simulate gravitational load. The exercise helps. It does not prevent bone loss entirely. Even with the best current protocols, astronauts return to Earth with bones measurably thinner than they left with. Now, extrapolate. A 20-year voyage to Proxima Centauri would expose a crew to continuous microgravity for 2 decades. Without effective countermeasures, total bone loss could exceed 50%. Skeletons would become fragile beyond use. A crew member attempting to stand upright under normal gravity at the destination would fracture their femur, their pelvis, their spine. The ship would arrive carrying functional biological cripples. Muscle wasting follows a similar trajectory. In microgravity, muscles atrophy because they are not required to support body weight. Astronauts lose about 20% of their muscle mass during 6-month missions, concentrated in the legs and back. Again, exercise helps. Again, the loss cannot be fully prevented. 2 decades of weightlessness would leave the crew's muscle mass depleted to the point of near paralysis. The cardiovascular system degrades differently but equally severely. Without gravity pulling blood toward the feet, the heart gets lazy. The body's fluid distribution shifts upward, causing the characteristic puffy face of long-duration astronauts. Blood volume drops, cardiac muscle weakens. When astronauts return to Earth, many cannot stand upright for hours or days after landing because their cardiovascular system has forgotten how to pump against gravity. Extending this adaptation across 20 years would produce cardiac deconditioning so severe that crew members might not survive the first attempt to step onto a planetary surface. The solution is artificial gravity. Rotate the ship around its long axis, and centrifugal force creates a simulated gravity pointing outward from the rotation center. Crew members living along the outer edge of the rotating hull experience something close to Earth gravity. Plants grow normally. Bones stay strong, muscles work. The engineering is not trivial. The rotating section must be large enough that the spin rate does not induce nausea. Small rotating habitats with radii under a few hundred feet make crew members dizzy because the Coriolis force affects inner ear balance. Experiments on Earth have shown that rotation rates above about 2 revolutions per minute cause persistent motion sickness in most test subjects. To provide comfortable 1G artificial gravity at a rotation rate below 2 revolutions per minute, the habitat radius must be roughly 700 feet. A starship with a rotating habitat that large is a massive structure, far beyond anything humans have built or launched. Generation ships and long-duration crewed vessels all incorporate artificial gravity in their conceptual designs. None of them exist. The engineering of a rotating space structure spanning a quarter mile has never been attempted in orbit. Bone loss is not the only long-duration threat to the crew. The mind, over 20 years sealed inside a metal hull, has its own vulnerabilities. Imagine the mission crew, 30 people, perhaps 50, selected from thousands of candidates for their intelligence, physical health, psychological resilience, and professional skills. The crew has trained together for a decade before launch. They know each other better than their own families. They have eaten the same simulated spacecraft meals, performed the same emergency drills, and argued the same arguments so many times that each person can predict what the others will say. Then they board the ship. The hatch closes, the laser fires, or the fusion drive ignites, and the ship begins its interstellar burn. The crew settles into what will be their entire remaining world for the next 20 years. The psychological research on long-duration isolation is grim. Submarine crews, after months underwater, develop predictable patterns of interpersonal conflict. Antarctic Research Station residents, wintering over in the darkness, experience a condition informally known as winter over syndrome, characterized by cognitive impairment, depression, and social withdrawal. Orbital astronauts, who rarely stay in space longer than 6 months, generally cope well with short missions but report significant emotional difficulties when missions extend toward a year. 20 years is uncharted territory. No crew has ever been tested under conditions of that duration. The Mars 500 experiment conducted in Moscow between 2010 and 2011 simulated a 520-day mission to Mars. 6 volunteers lived inside a mock spacecraft for roughly 17 months. They completed the experiment, but detailed analyses later showed significant psychological deterioration. Some crew members developed sleep disorders. Some became lethargic and withdrew from social activities. 2 crew members did not tolerate the isolation well and showed signs of clinical depression by the end. 17 months, less than 1/10 of an interstellar mission duration. The conflict problem is worse than simple boredom. Humans in confined groups develop rivalries, factions, and escalating grudges over trivial issues. On Earth, these conflicts are usually diffused by the option to leave, change jobs, move cities, stop seeing the people you cannot stand. On an interstellar starship, none of those options exist. A crew member who becomes unbearable to their shipmates cannot be sent home. They cannot be transferred to another ship. They cannot even be given physical space away from the others for any extended period. Every interpersonal conflict on the ship must be resolved within the ship by the same people who are the subject of the conflict. There is no outside mediator, no one they can call. Mental health professionals are 4 years away by radio, which means any advice comes too late to matter. Serious psychiatric illness presents an even harder problem. If a crew member develops severe depression, psychosis, or violent paranoia, what does the ship do? Confinement is possible for a short period. Indefinite confinement of a crew member for 20 years with no possibility of treatment or release becomes a form of living entombment. There is also the grief problem. Crew members launching from Earth will leave behind parents, siblings, friends, and in some cases children. By the time the ship reaches Proxima Centauri, many of those loved ones will be dead. News of deaths arriving by radio takes 4 years to reach the ship. The crew may learn that a parent died 2 years after the funeral, when the laser signal finally arrives. There's nothing to do, no way to attend the ceremony, no way to say goodbye. The grief is delayed, unreleased, and impossible to share with anyone who did not know the lost person, and radiation, meanwhile, is killing them slowly. Cosmic rays are a problem for electronics. They are a worse problem for humans. Outside the protection of Earth's magnetic field, a starship crew is exposed to a continuous shower of high-energy particles that damage DNA, kill cells, and elevate cancer risk. The dose rates are significant. Astronauts on the International Space Station receive roughly 100 times the natural background radiation of sea level on Earth. That is manageable for missions lasting months. Over years, the risk accumulates. Over decades, it becomes serious. A 20-year voyage to Proxima Centauri, with no magnetic shielding beyond what the ship itself provides, would expose the crew to a lifetime radiation dose roughly 10 times what is considered safe for professional radiation workers on Earth. Cancer risk scales roughly linearly with cumulative dose. A crew member receiving 10 times the professional limit faces a substantially elevated lifetime cancer risk. Some fraction of the crew will develop radiation-induced cancer during the mission. Ship-based medical facilities, limited by mass constraints, cannot provide the full range of oncology treatments available on Earth. Some cancers will be treatable, some will not. Crew deaths during the flight are a statistical certainty if radiation is not mitigated. The mitigation is shielding. Thick enough shielding can block most cosmic rays. The problem is that effective cosmic ray shielding requires enormous mass. Water works well as a shield because its hydrogen-rich molecular structure fragments incoming high-energy particles into less harmful secondary radiation. A water jacket around the crew habitat, several feet thick, can reduce the radiation dose to manageable levels. The mass penalty is severe. Several feet of water around a habitat volume large enough to hold a crew of 30 humans adds up to thousands of tons of shield mass. That water must be accelerated to interstellar speeds alongside the crew. Every ton of water is a ton of payload that requires additional fuel to accelerate, which requires additional mass, which requires additional fuel, following the same rocket equation logic that plagued the earliest chapters of this mission analysis. Lead or other dense materials provide some shielding by mass, but not as efficiently as water on a per kilogram basis. Specialized materials like polyethylene embedded with boron shield slightly better than plain water. No material provides meaningful shielding against the highest energy cosmic rays except sheer mass. Electromagnetic shielding, using superconducting coils to generate a miniature magnetic field around the ship, has been proposed. The magnetic field would deflect charged particles the way Earth's field deflects them. The required field strengths are staggering, however. Coils capable of protecting a habitat-sized volume would mass thousands of tons on their own, along with cryogenic cooling systems to keep the superconductors operational. The mass savings over passive shielding are marginal at best. Onboard radiation storm shelters offer partial protection. During periods of elevated radiation, such as a solar flare from the host star, or the ship's approach to certain interstellar regions, the crew retreats to a heavily shielded inner compartment. The shelter protects against the worst events, but cannot be used for routine occupation. Even with a shelter, the crew accumulates substantial dose during normal operations. Certain pharmaceutical countermeasures reduce radiation damage at the cellular level. Antioxidant compounds, along with experimental drugs that enhance DNA repair, show promise in laboratory studies. None have been tested across 20-year exposure durations. No one has ever tried. The radiation problem compounds every other life support problem. A crew that is sick, weakened, and immunologically compromised by chronic radiation exposure is less resilient to all the other stresses of the mission, and then they must navigate. The ship has launched. It is cruising at some fraction of light speed through interstellar space. Proxima Centauri is, optimistically, 4.2 light-years away. The ship must arrive at that exact point, not some other point, and it must arrive on a trajectory that allows the mission to do useful science. How does the ship know where it is? This is the navigation problem, and it is not as simple as looking out the window. Interstellar space has no landmarks, no GPS satellites, no ground stations broadcasting timing signals. The stars themselves are the navigation references, but over the course of a multi-decade journey, the geometry shifts. The ship's perspective on distant stars changes with its motion. Proxima Centauri itself moves against the background of more distant stars. Earth moves. The entire reference frame drifts. Conventional spacecraft navigate using radio tracking from Earth. Ground-based antennas measure the signal's round-trip time and Doppler shift, deriving the spacecraft's position and velocity with precision down to a few yards at the distance of Mars. This system works because the round-trip time is short. A signal to Mars and back takes under an hour. At interstellar distances, radio tracking becomes useless. The round-trip time to Proxima Centauri is over 8 years. Tracking data derived from an 8-year-old signal cannot steer a ship that has moved thousands of astronomical units since the signal left. The ship must navigate itself. That means carrying sensors capable of determining its own position by observing the stars, measuring their apparent positions with enough precision to calculate its location within the Milky Way. The technique is called stellar navigation, and it works, but only if the sensors and algorithms are accurate enough. The precision required is breathtaking. To arrive at Proxima Centauri within 1 astronomical unit, roughly the distance from Earth to our own host star, the ship must know its position at the end of the 4 light-year flight to a precision of about 1 part in 300,000. That means continuously measuring stellar positions to an angular precision of a few milliseconds, roughly the apparent size of a small coin viewed from across a continent. Onboard star tracking cameras can, in principle, achieve this precision, but only with very careful calibration. The camera itself must remain stable over decades. Any mechanical drift, any thermal distortion, any aging of the optical components introduces errors that compound over the journey. By the end of 20 years, a small calibration error at launch has grown into a massive positional uncertainty at arrival. The ship must also know its velocity precisely. Small velocity errors, integrated over decades of flight, produce enormous position errors at arrival. A velocity uncertainty of just a few meters per second, sustained over 20 years, results in a position error of billions of miles at the destination. That is enough to miss the target system entirely. Some proposed solutions use pulsars as reference clocks. Pulsars are rotating neutron stars that emit radio pulses at extremely regular intervals. A ship equipped with a pulsar timing receiver could use several pulsars simultaneously as a kind of galactic GPS. This technique, called X-ray pulsar navigation, has been demonstrated experimentally on Earth-orbiting spacecraft. Scaling it to interstellar distances requires detectors sensitive enough to catch faint pulsar signals across light years of interstellar gas. Even with perfect navigation, the ship must execute precisely timed course corrections throughout the flight. Each correction consumes fuel. Each correction must be planned and executed autonomously, without ground support, which leads to the final operational problem. Software. A starship bound for Proxima Centauri will carry onboard software that must function correctly for 20 to 50 years, with no possibility of a bug fix sent from Earth. The software must handle every foreseeable situation, every sensor glitch, every hardware failure, every navigation decision, every emergency, and every routine operation, without human intervention. This is an unprecedented demand. Every previous spacecraft has relied on ground control to identify bugs, develop patches, and upload fixes during the mission. Voyager 1 has received software updates multiple times during its 48-year mission, most recently in 2023, when engineers at the Jet Propulsion Laboratory uploaded a workaround for a memory fault that had scrambled the probe's telemetry. The fix worked. Voyager kept transmitting. Without that update, the mission would have ended. An interstellar probe cannot receive equivalent support. By the time a software problem is detected on Earth, the round-trip time for a fix is years. By the time the fix arrives, the probe has flown past its target or suffered cascading failures from the original bug. Writing software that works flawlessly for 20 years across all possible operating conditions is effectively impossible with current development practices. Even heavily tested flight software contains bugs. The Mars Climate Orbiter, lost in 1999, crashed into the Martian atmosphere because a unit conversion bug went undetected through multiple code reviews. The Ariane 5 rocket's maiden flight in 1996 exploded shortly after launch because a numerical overflow in the guidance software caused a cascade of errors that triggered the self-destruct system. The bug had been present in the code for years, but only manifested under the specific conditions of the maiden flight. Starship software will face conditions the developers cannot fully anticipate: interstellar dust impacts, cosmic ray hits on memory, sensor degradation from long exposure to vacuum, component aging, and countless other unpredictable events will affect the probe during its flight. The software must handle all of these without crashing, without entering an unrecoverable state, and without making decisions that compromise the mission. Formal verification, a software development technique in which the code is mathematically proven to meet its specifications, offers some protection. Aerospace industries use formal verification for the most critical flight software. The process is expensive, slow, and only works for well-defined subsystems. A full Starship software stack with millions of lines of code cannot be fully verified with current tools. Redundancy helps. Running 3 identical software systems in parallel, each computing the same result, and using voting logic to pick the majority answer, catches most single-event failures. The International Space Station uses this approach, so do modern commercial airliners. But all 3 systems running the same code will fail identically when they encounter a shared bug. Redundant hardware does not protect against software errors. Diverse redundancy, where 3 different teams write 3 different implementations of the same software, provides better protection. The implementations are unlikely to contain the same bugs. This technique is used in some aviation systems. It doubles or triples development cost, and it does not eliminate all failure modes. An interstellar probe must also handle hardware failures gracefully. If a critical sensor breaks, the software must reconfigure the probe to operate without that sensor. If a processor fails, backup processors must take over seamlessly. Every possible failure mode must have a planned response, and the planned response must be tested before launch. All of the above assumes that funding exists. It does not. The total cost of a serious interstellar mission, by current estimates, ranges from tens of billions to trillions of dollars. The low end covers a breakthrough Starshot-style laser array and swarm of gram-scale probes. The high end covers a Daedalus or Icarus-class fusion starship, complete with fuel mining infrastructure on the Moon and gas giants, along with orbital construction facilities for the ship itself. No government on Earth has committed to funding at this scale. The United States space budget is roughly $25 billion per year, split across a range of missions including the International Space Station, lunar return programs, Mars exploration, Earth science satellites, and dozens of smaller projects. Even a single year of the entire American space budget would fund only a small fraction of the cheapest realistic Starship proposal. And the Starship would need sustained funding across decades, not a single year. The Chinese Space Agency has grown rapidly in recent years, but still operates at a similar budget scale. The European Space Agency, the Russian program, the Indian, Japanese and other national programs combined still total less than $50 billion annually across all spaceflight activities. Diverting the entire world's space budget to a single interstellar mission for a decade would approach the required total cost for breakthrough Starshot. No political mechanism exists to make that diversion happen. Private funding has stepped in at modest levels. Yuri Milner's $100 million commitment to breakthrough Starshot was the largest private investment in interstellar research in history. That funding has not been renewed at similar levels since the initial announcement in 2016. A report published by Scientific American in September 2025 described the project as quietly winding down, with key researchers moving on to other work. Elon Musk's SpaceX has publicly focused on Mars rather than interstellar targets. Jeff Bezos's Blue Origin has focused on lunar operations and Earth orbit infrastructure. Neither billionaire has committed significant funding to interstellar projects. The private sector's interest in spaceflight remains concentrated on nearer-term commercial opportunities, not multi-generational scientific missions. The time horizon is the political killer. A Proxima Centauri mission, from funding decision to first data return, would span at minimum 40 years. More realistically, 60 to 80 years. The politicians who authorize the spending will be long out of office, or dead, by the time the mission produces results. Electoral cycles do not reward multi-decade investments that pay off after every current voter has died. Scientific organizations face similar problems. Research programs in particle physics, which sometimes span several decades, struggle to maintain funding continuity across administrative transitions. The Superconducting Supercollider, a massive particle physics facility proposed for Texas in the 1980s, was cancelled mid-construction in 1993 after congressional budget pressure. The partially completed tunnel was sealed. The program's scientific ambition was absorbed by European projects. An interstellar mission would face similar vulnerabilities across its multi-generational lifespan. There are proposals for international consortia, treaty-based funding structures, and endowment-style long-term investment mechanisms. None of these have advanced past conceptual discussions. The funding structures for century-scale scientific projects simply do not exist in current political or economic systems. Which is a shame, because the destination itself may not be worth the journey. Assume for a moment that humanity solves the funding problem, a global consortium forms, resources are pooled, $100 billion per year is allocated to the program, sustained across 40 years. Construction begins, the ship launches. Then consider what could go wrong after departure. Not during construction, after. A single component failure in the fuel ignition system halfway through the flight. The ship limps to the destination at reduced velocity, arriving decades late, with insufficient fuel for the planned braking maneuver. The crew is still alive, but the mission profile is destroyed. A cosmic ray strike in year 12 corrupts the navigation computer's memory. The backup systems vote in a faulty correction. The ship's trajectory shifts by a fraction of a degree. By arrival, the ship is 1,000,000 miles off course, sweeping past Proxima Centauri at relativistic speed with no possibility of returning. A hull breach in year 7 from a dust grain larger than the models predicted. The breach is small, but repair crews cannot reach it before one section of the habitat loses atmosphere. 12 crew members die. The survivors continue the mission with reduced capability, grieving, demoralized, and short-handed for critical operations. A software bug that escaped testing manifests only under specific thermal conditions. The bug corrupts the life support control system. Oxygen levels drift outside the safe range for 3 days before the crew notices. Several crew members suffer cognitive damage. The medical officer, one of the affected, cannot diagnose the problem accurately. A political collapse on Earth during the flight. The consortium that launched the ship dissolves. Ground communications with the probe are discontinued because no one remaining has the budget or institutional authority to operate the receiving array. The ship is still functioning, still transmitting, but no one is listening. The crew, informed of this by the last transmission they receive from home, must decide whether to continue a mission for a civilization that has forgotten them. Every one of these failure modes is plausible. Several are likely over any mission lasting longer than a decade. The cumulative probability of at least one catastrophic failure across a 20 to 50-year interstellar mission is close to certain with current engineering practices. Compare this to the outcome statistics for actual deep space missions. Of the two Voyager probes, both are still functioning after more than 45 years, although at reduced capability. Of the Pioneer probes, both eventually went silent, Pioneer 10 in 2003 and Pioneer 11 in 1995, due to power decay in their radioisotope generators. Of the Mars Observer spacecraft, lost in 1993, the cause of failure was never determined. Of the Mars Climate Orbiter, lost in 1999, the cause was a software bug. Approximately 1/3 of ambitious planetary missions fail before completing their primary objectives. These are missions operating in a relatively forgiving environment, close to Earth, with continuous ground support. An interstellar mission, operating without ground support for decades, in a far more hostile environment, faces failure rates that are arguably much higher. The mission might succeed. The probability is not zero, but the probability of success is not high enough to justify the investment on purely scientific grounds, unless the destination offers something uniquely valuable. Which brings us to the destination itself, Proxima Centauri B, and what it actually is. Proxima Centauri B was discovered in August 2016, announced in a paper published in the journal Nature by Guillem Anglada Escudé and 30 colleagues. The discovery team, operating under the project name Pale Red Dot, used spectroscopic data from the HARPS instrument at the European Southern Observatory in Chile. They detected a tiny wobble in Proxima Centauri's motion, caused by the gravitational pull of an orbiting planet. The planet's parameters, as best we can determine from Earth-based observations, are provocative. Its mass is at least 1.17 times that of Earth. It orbits Proxima Centauri every 11.2 days at a distance of roughly 4.6 million miles. That is about 1/20th of the distance between Earth and our own star. At first glance, this sounds far too close to be habitable. Anything that near to a star like ours would be a vaporized rock. But Proxima Centauri is not like our star. It is a red dwarf, a dim cool star that radiates roughly 1/500th as much energy as our own. Because the star is so dim, its habitable zone, the range of distances where liquid water could exist on a planetary surface, is much closer in. Proxima Centauri B orbits within this habitable zone. Its average surface temperature, if the planet has an Earth-like atmosphere, could support liquid water. This is why the discovery electrified the astronomy community. The closest star to our own system, a mere 4¼ light-years away, has a potentially habitable planet. The coincidence is almost suspicious. Of all the nearest stars, the very nearest one happens to host a world in the habitable zone. The problem is that potentially habitable does not mean actually habitable. And Proxima Centauri B has several features that make it a probably hostile place. The planet is almost certainly tidally locked. At its close orbit, the gravitational interaction with Proxima Centauri has likely synchronized the planet's rotation with its orbital period. One side of the planet faces the star permanently, while the other side faces away into eternal darkness. The day side would be baked in constant red starlight. The night side would be frozen at temperatures approaching absolute zero. Only along the narrow terminator zone, the ring where day meets night, would temperatures permit liquid water. Tidal locking affects atmospheric circulation in brutal ways. Heat from the day side drives constant winds toward the night side, where the gases cool and freeze out onto the dark surface. Over time, the entire atmosphere could migrate to the night side and condense into ices, leaving the day side airless. Detailed climate models suggest this is a real risk for Proxima Centauri B. The planet might not have a magnetic field. Planetary magnetic fields protect atmospheres from stellar wind erosion. A tidally locked planet with a weak or absent magnetic field could have lost most of its atmosphere over billions of years, stripped away by radiation from its host star. Observations to date cannot confirm whether Proxima Centauri B retains a substantial atmosphere or has been stripped bare. A probe arriving at Proxima Centauri B might find a live world, full of oceans, clouds, and potential life. Or it might find a dead rock, scorched on one side and frozen on the other, barely worth the cost of photographing. Red dwarf stars have a habit that makes their habitable zones much less habitable than they appear: flares. A flare is a sudden brightening of a star's surface, caused by magnetic field lines snapping and reconnecting in the upper atmosphere. The release of energy blasts radiation across the electromagnetic spectrum, from radio waves through visible light into ultraviolet and X-rays. Our own star produces flares occasionally. They sometimes disrupt radio communications on Earth and rarely damage satellites. For the most part, our star is calm. Red dwarfs are not calm. Proxima Centauri specifically has been observed flaring repeatedly, often with energies comparable to the largest flares our star has ever produced. In March 2016, a telescope at the Everscope Observatory caught Proxima Centauri producing a flare that brightened the star by a factor of 68 in visible light. For about 10 minutes, Proxima Centauri was more than 10 times brighter than normal, releasing energy in all directions. The estimated radiation dose delivered to Proxima Centauri B during that flare was roughly 4,000 times the dose Earth receives from the largest flares our own star has ever produced. Any life on the surface of Proxima Centauri B during that 10-minute event would have been exposed to ultraviolet and X-ray radiation at levels far above what unshielded organisms can survive. The flare was not unique. Proxima Centauri produces flares of similar magnitude with some regularity. Analyses suggest that major flares occur every few years and smaller flares happen weekly. Over the 4.5 billion years of Proxima Centauri B's existence, the planet has been bombarded by millions of significant flare events. The cumulative effect on any atmosphere is severe. Each flare ionizes the upper atmosphere, stripping away lighter molecules. Over geological timescales, most of the planet's original atmosphere may have been lost to space. If Proxima Centauri B ever had a water-rich atmosphere, it may have been flare-eroded down to a thin residue of heavier gases. The effect on surface life, assuming any exists, is worse. Without a thick atmosphere and magnetic field to absorb the radiation, flare events would deliver lethal doses to any biochemistry based on DNA or similar molecules. Extremophile microbes might survive in subsurface environments, sheltered by meters of rock or ice. Complex surface life appears unlikely under these conditions. Our probes, if they arrive, will face the same radiation challenges. A flare during close approach could damage the probe's electronics beyond repair. Mission planners would need to time the flyby during periods of predicted calm, which is difficult given that Proxima Centauri's flare patterns are only partially understood. The image of Proxima Centauri B as a cozy Earth-like world is almost certainly wrong. The planet is more likely a battered, flare-scoured rock, with a thin atmosphere and a surface hostile to unshielded life. Images from a flyby probe would probably show a dimly lit day side under a red glare with deep shadows and a frozen night side. Beautiful, perhaps. Earth-like, probably not. All of this leaves the fundamental question unchanged. Is this destination worth the voyage? Every chapter of this mission briefing has been a catalogue of reasons why reaching our nearest star is currently impossible. The distance is too great. The propulsion technologies do not exist at request scale. The fuel supply is inadequate. The laser infrastructure is unbuilt. The deceleration problem is unsolved. The communication delays are unworkable. The life support systems cannot maintain closure for decades. The crew psychology breaks down. The radiation exposure accumulates beyond survival. The navigation precision is beyond current sensors. The software cannot be guaranteed bug-free. The funding does not exist. The destination may not even be worth visiting. And yet teams around the world continue working on the problem. Funding continues to trickle in. Papers continue to be published. Conferences continue to be held. The British Interplanetary Society, still active after more than a century, continues refining the Icarus blueprints. Philip Lubin's research group at the University of California continues improving laser propulsion designs. NASA's Innovative Advanced Concepts program continues funding small studies of exotic propulsion ideas. The breakthrough Starshot team, though quieter than before, has not formally dissolved. The question is why. Part of the answer is that humans do not give up easily on questions that matter. Reaching another star is one of the defining questions of our species. If we can do it, the implications for human civilization are profound. We become a multi-star species. We learn about planetary systems beyond our own. We acquire the technological base needed to survive whatever might happen to our home system in the long term. The questions are worth trying to answer, even if the answers take centuries. Part of the answer is that technologies developed for interstellar missions benefit nearer-term goals. The fusion propulsion research for Icarus is directly applicable to interplanetary missions that would shorten Mars travel from months to weeks. The laser infrastructure for Starshot could propel probes across the solar system at unprecedented speeds. The life support systems needed for generation ships could support permanent lunar and Mars colonies. The software verification techniques required for 20-year missions could improve reliability of everything from medical devices to power grids. Part of the answer is that failure modes can be studied in isolation. Perhaps the full interstellar mission is not achievable today, but a submission, a flyby of an object in the Oort cloud, or a probe sent to the gravitational lens point of our star at 550 astronomical units, can be attempted with technology closer to current capability. Each successful submission advances the state of the art and makes the full interstellar mission incrementally less impossible. There is also the darker argument. A species confined to a single star system is vulnerable to any catastrophe that affects that system. A supernova in the galactic neighbourhood, an extended period of asteroid bombardment, a failure of the long-term habitability of our planet, any of these could end human civilization permanently. Spreading to other stars is not merely an adventure, it is a survival strategy for a species betting on a long future. The math says no. The humans keep trying. This pattern has played out before in the history of mountaineering, polar exploration, deep-sea diving, and rocketry itself. Each of those fields began with similar analyses, similar lists of reasons why the goal was unreachable. Each of them eventually succeeded, decades or centuries after the original attempts. The stars may yield on the same timeline. Not tomorrow, not this generation. possibly not within the next 2 or 3, but eventually someone, somewhere, will receive the first low-resolution photograph of Proxima Centauri B, beamed across 4 light-years of vacuum by a probe that humans sent out, waited for, and finally heard back from. The mission briefing ends here. The voyage, if we choose to undertake it, begins whenever we decide the math can be beaten.